On my phone, it's only an hour and 21 minutes. But when I like pulled it into iMovie or whatever, I was trying to get it out and trying to play it on through my phone. It's like 7 hours and 30 minutes long, and I'm like, so there is that. Nathan, when are y'all gonna start traveling?
So I think February 19th our first game, and after that, I think we're at home the first weekend, and then after the next weekend we'll go somewhere. We actually play Mississippi State the third weekend.
Really, when?
We're going to Mississippi State March 5th through the 7th. It'll be fun. I got I told you I live near there. I got some buddies that play on the team, and
Oh, I'm going for that.
go for it.
I'm going back for that. Yeah, no doubt. Have you ever been to Davis Wade? I mean, it's not Davis Wade.
Duty
Noble.
In high school, I had some tournaments there. I have played on that field, but not the new, because they redid it all. I
They
haven't been down
redid
there.
everything, bro.
That looks
It's
beautiful.
top notch.
Yeah.
Like,
Yeah. Did you ever go to games? I guess while you were in.
I did. I went to a few of them. Like, I mean, it's just, you know, baseball can be tough to watch.
Yeah.
Mississippi State is like the Cubs of college and everything. So, me and Mississippi State sports have a love-hate relationship. I love Mississippi State. I just hate watching the sports because, man, they break my damn heart every time.
Especially football.
Especially in football. So, I don't get very excited about Mississippi State football because I don't want to get my heart broken at the end of the season.
Well, the baseball team's a lot better than football. So
But the baseball team is good, man. Then they go to the World Series and they're like, yes, we're gonna, and then so.
I guess you were there when Brent Rooker was there. You remember him?
Mm-hmm.
See, I graduated with his brother. We went to the same high school, and I'm good friends with him and his brother and everything.
That's awesome, y'all are playing. I'm gonna have to go back for that. Where
my
I'll
boss,
get a half shirt, one of those house divided shirts.
The guy I worked at Helena with, my manager or whatever, he said, because he's a diehard Mississippi State fan, he went there, his dog goes there, he said, he found out we were playing him, he said, man, I'm being left field throwing chicken wings at you.
So, funny story about that, we actually were playing, we hosted some regional or whatever, and so every once in a while you have to switch dugouts.
Yeah.
So now they were home, and they were in left field lounge with the bullpen right there, and so everyone in left field lounge was like looking up on their phone, checking out their Facebook, talking about their girlfriend, like just clowning on them, you know, because that's just kind of what they do, you know, like all in good fun, like it wasn't anything over the top. And then finally it was like, all right, here's some food, like, you know, but you don't ever get the opportunity to be on the other side of that. That's awesome, man. That made my day.
They had I really like the old cars they had out there in the outfield. I wish they kept some of those. But
they got some stuff, man. Again, it's land grants in your Mississippi State. Whatever. That's awesome, man. I was not having a great day this morning.
I'm glad I cheered you up.
That actually kind of made me a little bit like excited. So I was talking with most of the class earlier. Was that even though I'm looking over most of the stuff and trying to figure out some things that in soil chemistry and in soil water conservation, like it's all kind of redundant, but it's meant to kind of drill those things into your brain so that you kind of get an understanding. And so I thought about that whole pH dependent charge kind of thing, and I realized that I probably could have set that up a little better with some a little bit of intro about acidity. So maybe we can get back to that. Everyone seemed to be pretty good on isomorphic substitution, right? We're going to just have the change between silica and aluminum in the tetrahedral layer, and we're going to have a change of aluminum and magnesium in the octahedral layer, okay? And so most of this happens during formation. There's probably not a whole lot of note-taking going on, but it's going to revisit some concepts. And you can see that the charge changes about 4. We go from having this overall net charge being negative 12. When we substitute, we get the change to negative 22, right? So we kind of like a bank account. We had 12 up here, and now we went to 9. We had 12 there, and we went to 8, and then 12 again to 9. and we get a net change in charge of 10 centimoles of charge per kilogram. I know this is going back for soils, but just to go over that again. So some of the reasons why soil acidity is important, mostly when we're talking about fertilizers, the nutrients are available at certain pHs, right? And then this is also going to get into, and I think what we're going to do on Thursday is talk about how the pHs change the molecules and how they're adsorbed to the soil. So that's going to actually tie that in and make that an application type deal. So not only are we got some fertilizer wasted because we put it out there, all the charges, all the negative charges on the soil colloids were taken up by hydrogen. And that is what I'm going to show in a moment. Familiar? Coming back a little bit. I'm going to post these online. I also think I'm going to post the videos other than the 7-hour and 39-minute video. I did it on slow-mo on my phone. So the first part is like, hey, yeah, and then it goes to...
Oh, that's funny. I was wondering what you're doing with it.
So, but I think a YouTube video is like a YouTube playlist that has just yours, so you can click on the link, go straight to it, and there's no link. So, pH being the log of the hydrogen concentration, these brackets, whenever you see brackets, that means concentration. And so I'll use that more often instead of writing out concentration. There are some classifications of what we determine acidic and alkaline, and something that I was mentioning in my soils class, that the change between 4.5, or the change between very strongly acidic and strongly acidic, we can technically term this becoming more alkaline, because we're heading towards 7, kind of like the arrows, like integers. We're becoming more positive as the number increases on the positive side. As it decreases towards the negative side, it's becoming more negative. Positive 4 being more negative than positive 5. Okay, so you'll hear me use the terms as it becomes more alkaline. So I may be talking about a change in pH that's only a half of a pH point, but it's becoming more alkaline. Becoming more alkaline. If we go the other way, then it's becoming more acidic. I'm sure many of you have seen this pH scale. Baking soda is something, baking soda and ammonium, or ammonia, sometimes it's ammonium hydroxide, the OH being a hydroxyl. These two things I consider easily to be alkaline. Alkaline is going to have a very soapy kind of feel to it. It's going to be like a lubricant, almost, like oil. I had a thing one time, I had ammonium hydroxide and I had water next to each other. And I couldn't remember which one was which. And I spilt some on like a brown paper towel, and I didn't know. And so I went and I put my finger in and I put it on my tongue. And I instantly knew which one it was. It was the ammonium hydroxide. I felt like I had a 9-volt on the very tip of my tongue. And you know, the only way to neutralize that is to go get an acid. And I just could not bring myself to go, you're about to put acetic acid on your tongue. Doesn't make it, after you just put ammonium hydroxide on your, you might want to think about that a minute. So I just had to use water to get that off. And then we're starting to move towards more acidic. So the pH in pure water, which we very rarely have because there's always some sort of contaminant. It may not be like a pollutant, but there's some contaminant. It's not pure. And so the the hydrogen concentration, H+, and the hydroxyl concentration, OH negative, needs to equal, those exponents need to equal -14. Making sense? Following a little bit? Okay, good. So, technically what we're measuring is we're measuring the concentration of this hydrogen ion. That's what we measure with pH. Okay, so we have water and there's this hydrogen ion that associates with the water to form this hydronium ion. And then instantly this hydrogen will dissociate and come up with another one, and we can measure the activity and the movement of the hydrogen. So, as our pH is increasing, the hydrogen concentration is decreasing. At 10 to the negative 9, there would only be a whole bunch of zeros and then this one little hydrogen sitting out on the end, right? So, remember, we said that it's both the hydrogen and the hydroxyl. So if we don't have a lot of hydrogen, what do we have a lot of? The hydroxyls. And then vice versa. As pH decreases, because as our pH decreases, this number is much greater. So we have a lot of hydrogen as our pH decreases. You remember those? Okay. So as one pH unit changes, so from 5 to 6, there's a 10x change in acidity and alkalinity. Whether it becomes more alkaline or more negative. Remember, because it's on a log scales suck because you can't ever really make heads or tails of those. The lines change, they're not very square. It takes some extra thought processes to interpret a log scale graph. So if we had a pH that starts at 7 and we increase the hydrogen concentration by 100, we will go from 7 to negative 6 would be 10, and then 7 to negative 5 would be 100. So we go from 10 to the negative 7, 10 to the negative 5, and remember both of these have to equal 14. And so if we have a lower exponent, our hydrogen concentration is correct, it is greater. Therefore, this is what our pH equation would be. So as the number decreases, the concentration increases. Just backwards like that. Some of the sources, I guess, that we kind of go over, and I had this from soils, is explaining how this hydrogen will dissociate off of this hydroxyl. This hydrogen can dissociate with aluminum. We have a hydrolysis reaction, dissociation of the hydrogen ion. We have, not that you're going to need to know this, you won't have to write out Gibbsite, but there's going to be an extra hydrogen out here in the soil. And as we increase our hydrogens, what happens to the pH? Up or down? It goes down. Okay? So the pools of acidity are going to be active, exchangeable, and residual. So active is kind of what's floating around in the soil solution. This is easily fixed with lime. Exchangeable is what's actually attached to the soil solid phase. That's going to require an exchange reaction. We're going to have to add some other cation to exchange that hydrogen off, typically calcium, because we can get 2 hydrogens off with 1 calcium cation. And then finally, the residual is what is inside those clay layers, and it's really difficult. That is what kind of supplies. It's like the endless supply of hydrogen and aluminums that just, once the concentration decreases in the soil solution and the solid phase, it just sends the reinforcements kind of. non-exchangeable being what is held, and look, this is what we will call the diffuse double layer. There is a certain field of attraction for those ions. And then finally, the residual activity that is inside the clay structure, that is inside that tetrahedral layer. So remember, we had, in that isomorphic substitution, we had Al3 plus, right? Well, that Al3 plus is what comes into the soil solution and contributes to the acidity of the soil. Right here, this non-exchangeable form in the lattices of the clay minerals. So as weathering processes break down those minerals, that aluminum is then released into the soil solution. Questions so far? I'll make sure I post these notes too, along with the videos. And that'll be how you won't miss anything in class when you go to do your stuff.
I was going to tell you about that, after class or something.
Yeah, no, they said.
I was going to say, our athletic advisors will send out like when we're.
They did. I got the email.
Okay, I'll tell you. Well, you should know anyway. Because I'm not in class. I'm doing baseball. If I'm not in class, I'm at baseball.
Yeah, sure. Well, that's the great thing about it, is that I'm always going to post everything online. So I have students that are like, "I'm going to be out of town. I'm so sorry for the inconvenience." I'm like, "You need to go spend time with your family. Class will be here when you get back." Okay. And so sandy soils and clay soils have more exchange sites, therefore the potential and the residual acidity would be greater. And it would require more tons of lime. And you'll get that back on a soil test report. When you send out your soil test report, they'll send it back and they'll tell you what the acidity is and how much lime. And you'll be able to see that you don't need as much. You don't need as much lime to neutralize this, because there's only so many exchange sites on sand particles. The sand is, it's a little, they're big, they just don't have much charge on them. And so it's easier to neutralize this active acidity, because if it's not on the soil colloid and it's not in the soil colloid, it's out in solution. So we can neutralize that fairly easily. Just remember, clay soils are going to require more lime than sandy soils. We went over this aluminum hydrolysis. Now, back to pH-dependent charge. 3 sources of pH-dependent charge are
Aluminum iron oxides.
functional groups of organic matter,
Aluminum and iron oxides.
aluminum and iron oxides, and broken edges of clays. Okay? The broken edges of clays, that's electron microscope, that's scanning electron microscope type stuff. That's way beyond the scope of what we're doing here. So functional groups of organic matter, aluminum and iron oxides, broken edges of clays. Likely to be a test question. So not so much that you need to remember that these are a carboxylic group or a phenolic or an alcoholic group. Just that these functional groups have this hydroxyl on the end. However, the hydroxyl is balanced, right? There's no charge on this because everything in this functional group has now taken out the charge. So as we add lime, we all know we add lime to increase the pH or make the soil more alkaline. So as it becomes more alkaline, we have increased the hydroxyl concentration, right? Because remember, hydrogen is acidic, hydroxyl is alkaline. So if we have a high alkaline concentration in our soils, the hydrogens from the functional groups of the hydroxyl will dissociate and bond with the hydroxyls to form water. And when we're talking water, we're talking about a molecule, not like something that you could go extract. So there is this, do y'all remember Avogadro's number? 10 times, what,
6.23 times 10, no, it's
6.02
2
times 10 to the 23rd, correct. So it takes that many molecules to equal 1 gram of water. So we had this dissociation from these functional groups onto the hydroxyl concentration, and therefore now this oxygen has a negative charge to it. And since we have more negative charges, we can now hold on to calcium, magnesium, potassium, ammonium. Catch up. Catch up. All right. So now that we have all these water molecules floating around, and we have this negative, we have this increased negative charge on this functional group of organic matter, this being the organic matter. If we have acidic soils with a greater hydrogen concentration, so as we apply lime, and I want to take this straight to crops. You do a soil test in February, you know what's in there, the soil test results come back and say, hey, you need to apply such and such lime. You need to apply such and such lime. And now I want y'all to think about this in terms of what's about to happen in the soil based on what we do. You need to apply 2 tons of lime to the acre. We add lime, the soil becomes more alkaline. When the soil becomes more alkaline, like, so by the time that change happens between February and March, April, when we're starting to apply this fertilizer, those hydrogens will dissociate and form water in the soil solution, leaving these negative charges right about the same time that we're coming in and putting out an ammonium fertilizer. Urea. Urea undergoes the hydrolysis process, forms 2 ammonium. That ammonium attaches right here, 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 and here. So we're increasing the CEC of the soil. Next, we come out and we apply our lime, we apply our fertilizer. The changes happen, and the change going from ammonium to nitrate, we lose hydrogen ions into the soil, which makes our soil more pH goes down. It's more acidic, correct. So now we have all these extra hydrogens floating around in the soil. And what happens? Because we need to get to this equilibrium where everything's balanced, that hydrogen will now reassociate with the hydroxyls that were on the functional groups of organic, the oxygen on the functional groups of organic matter. So there's this back and forth thing that's constantly going on with your soil as you're applying lime, as you're applying fertilizer. This change is constantly happening. And what soil chemists do is they measure and they calculate the change, and they'll sit in the lab and we can do some equations to figure out what the ion concentration and activity is. And how about we're going to go plant some stuff, we're going to put some fertilizer on it, and we're trying to keep it in the soil, not in the water.
I read something the other day. It was talking about like split shotting nitrogen, and yeah, it said in the field's fallow, it's more likely to leach out into some water sources or something like that. Well, why wouldn't, I can't remember if it said it or not, but why wouldn't you just wait until there's a crop in the field to keep most of it in the field instead of just wasting your fertilizer when there's nothing planted yet?
So they were applying a split shot when there was nothing in the field?
Yeah, or I was reading it. I wasn't like, it wasn't, I think that's what it said. I was just reading it and it said something like that, put some on before the crop's in or growing and then put some on after. You know why they, just go ahead and waste most of that oxygen that would leach out into the water? Or
Okay, so I guess the question that he's asking is why do we do a split shot of fertilizer?
yeah, pretty much. Yeah,
that's it. And
I didn't know if it was just nitrogen that didn't stick into the soil, or if it was a bunch of different fertilizers.
Are y'all good on this? Because I'm going to get to you. Are y'all good on this right here? make sure that I'm.
Yeah, you're in it.
Where's my window at?
You're good.
Still in? Y'all can see the
you're
whole
all
screen?
in.
I think
Cool.
you have the whole left side for it.
All of this
Yeah.
cut over to here?
You're a little
That's
out.
out, that's out.
Yeah.
Yeah,
That's
that's
good.
good.
Okay. So, in the beginning, what we're trying to do is we're trying to get this, you want to have some nutrient. Nutrient demand is greatest at about V7 and V9. Somewhere between V7 and V9, about V8. So if we apply, and let's say our rate is 200 pounds. 200 pounds of in. We wouldn't want to put all 200 pounds of in the beginning, right? Because it would leach out. You're exactly correct with that. So what we do is we apply a small portion, it's called a side dress application. This is the starter, this will be the side dress. So we'll apply 50 pounds. 50 pounds of in per acre. It's actually probably less than that. Pre-plant. So that by the time you apply ammonium or you apply urea, it has to undergo this urea hydrolysis process that eventually gives us ammonium. The ammonium will be attached to those negatives. As the plant starts to grow, so this is pre-plant, we put out 50 pounds of in. As the plant starts to grow, we kind of give it a little bit of nitrogen so that it can perform photosynthesis and it can start to, the roots can grow, the leaves will come out, they'll start doing photosynthesis and making more. So it's kind of like a pre-workout. As we continue on throughout the year, right here, we'll put this out pre-plant, V1. Next, we'll put out our other 150 pounds of in. Side dress, actually at V5. Because between V5 and V7, we have to undergo the same process as the pre-plant. So the urea has to undergo hydrolysis. The hydrogens have to find their place on those soil colloids. That's why we apply lime, so that we can open up those negative charges, or we can increase the potential for those negative charges. And then we're going to apply the majority of our fertilizer right here, because remember, we've got these really big tall plants in the field, and they all need nitrogen, and they're all going to need it right there. So we would apply a side dress to kind of preserve, and it's also raining a lot at the beginning of the season. So if you put all 200 pounds out, most of it will leach out because the soil can't hold 200 pounds of nitrogen as ammonia. At some point, there's no capacity for it.
Yeah. And then it's like also saying that nitrogen has nowhere to go, such as, at stage V7, has crops in the field, and nitrogen can go into the corn instead of just leaching out because nothing's there, right? At V1, I mean, like that's why you don't put all 200 pounds on it again. Okay.
Correct. And so here's what happens at another reason why, and here's the chemistry behind that, is because what happens here, Michaela, when we have long story short, 1 week worth of lecture short, we're going to eventually form nitrate. This is actually undergoing an oxidation, and we'll go over that when we get to that chapter, right? You remember that, Michaela? Coming back?
Yeah.
Are you kind of like, you got nightmares yet?
Yeah, I know that will leach out because it's negative and it won't hold.
Bingo. This is why, because this process is happening. Because after it stops raining, eventually the microbes will turn ammonium into nitrate through some process, this oxidation and ammonium oxidation, these bacteria, and when it's negative, it's not held to the cation exchange capacity, right? So if we only put a little bit out here, it's kind of like I saw in one of the videos that I showed my class yesterday, the difference between having a big cup and having a little bitty coffee cup. And having a little bitty. So if we have a clay soil, we can put a lot of nitrogen out, and there's enough negative charges that the soil will hold on to that. If we were to put it out in this cap, that was the CEC of our soil, we wouldn't want to put all that into that very small cap. So we have to spoon feed that over time. Okay, we have to spoon feed it so that we can make sure that A, we put the nutrients where they need to be for the plant to take up in the right amount. So that's the right rate, the right source, at the right time, and in the right place. So that slowly over time, like, the plant will still continue to grow with the nitrogen that's there, but we also want to use it up so that as this ammonium is taken up by the plant, we start to leave that negative charge for the next time that we come to refill with our big load of nitrogen.
I remember too, or I think it was when I was there this summer, just kind of early in the spring, we barely put any on because we're right next to the Mississippi River, just a bunch of sandy different soils all up in there. So I remember all that. Now that makes sense. So.
You come back?
Yeah.
Yeah?
Having flashbacks.
What's that?
Having flashbacks.
Having flashbacks? Do I need to come teach the nitrogen cycle for your grain crops class or forage crops? No. We probably wouldn't have this so much in a pasture system though, but just to understand that if you put urea on top of the soil, because you can't knife it in, that when you put urea on top of the soil, we're going to get ammonia volatilization through the same process. Right? That's why we kind of went over that. You have organic matter and you've got this dew that's on the ground, and if it doesn't rain and get it into the soil, it's going into the atmosphere. Excellent question, Nathan. I'm glad we got to explain that. Cassie, you okay?
Yeah.
You good?
Yeah, it's processing.
Okay. Maybe I'll go over this a little bit more in when we go over oxidation. I'll try and give a refresher into the nitrogen cycle, since y'all just came out of soils where you just filled in some stuff. You filled in the blanks. You hope that you got them in the right spot.
Wasn't there a chart like this that you used like close to the end of the semester where you talked about the right rate, right source, right time, right place? Wasn't there a chart almost like that where it talked about the?
There was.
Okay.
There was. I mean, I can pull it up.
That's what was kind of processing. So like I thought he kind of. Yeah. Starting to come back now, right?
I thought it was familiar.
Uh-huh. I probably could have went straight from there. So going back again, we only need so much right here, right? Because the plant is only growing, and you can see we only need to apply about a quarter of what our overall rate overall is needed to be. And therefore we need to apply the other 75% somewhere right here. That plant will continue to grow and that nitrogen will be available up until about tassel. And there's some research wanting to go on about flying over a tassel shot. I guess somewhere between here, between V6 and, you know, V11 or 12, so that you can still continue to supply this nitrogen. And my master's research was on being able to apply that single shot, being able to apply your full rate right here with some nitrogen stabilizers, so that we kept it as ammonium in the soil. We slowed down the urease activity, the conversion of urea to ammonium, and then we stopped the nitrification process where we kept the urea that converted to ammonium as ammonium throughout this whole growing season, especially in the Delta and Mississippi, and I guess in Tennessee too, even though I don't know.
West Tennessee, like, kind of just like the Delta, pretty much.
Sure.
It's pretty close.
Well, and where I have the problem as a professor is coming from row crop
Yeah.
to Middle Tennessee, where it's either some sort of vegetable or pasture. I'm going, where's the corn at? I got that. I could go over to West Tennessee and be right at home. So I'm having to kind of gauge over onto this pasture and forages and crops that I'm not overly familiar. I don't even know how to. I wouldn't know. I don't know the process, the timeline. When do you plant it? When do you fertilize it? How do you know when to cut it? What's the cutting process look like? I know they got the wind rake, and you hope and pray that they got a round baler, not a square baler. That much I know. Okay, I do know you don't want to mess with square bales. All right, I did that once, and then I did not volunteer for that again. So that's about the extent of my knowledge of pasture production. But over in the Delta, I got this all day long.
Say you plant corn like early June, but like really late. Would it be the same like process? You put a little bit of fertilizer on at the beginning, or would you put a lot more on since it's late in June when you planted?
So if you were to plant corn late in June,
Yeah, say for like, I don't know, a duck hole or a deer, you want to keep the corn out, you know, throughout the winter. Keep it later.
okay, so yeah, so you can shift that planting date to maybe mid-May,
Yeah.
maybe beginning of June. Yeah, sure, you would still kind of do that. Also remember that you have a weather pattern. Also remember that you're not growing it for yield.
Yeah.
So
I
you-
guess it's not that big of a deal.
So you wouldn't want to put 200 pounds out. You'd want to put like 170,
Yeah.
150, because, and maybe in 2 doses. And especially since in Tennessee it seems to be the same as Mississippi, where it stays warm till about January. So you might be able to do that. You would have to go back in and look at what the growing degree days are, and you would have to go back in and calculate and kind of think about when it was going to reach these growth stages. But if you applied a stabilized fertilizer, you could just plant your corn, a slow release, put it out, and be okay to go. Like, I would love to get into that. I'll be looking into doing something like that over the summer as like a consultant. Go in, take the soil samples, get the soil test. We're going to plant corn. We need to do this, do that. Fly, take my drone, fly some stuff. I just watched this cool video from like Delta Valley Outdoors. That video was legit. They had some really good fast motion shots, and it was just an outdoor channel basically. And so those are things that people are going to want, because it takes a lot of work to do that. What are the 3 sources of pH dependent charge?
Aluminum and iron oxide.
Okay, we're getting there. All right, aluminum and iron oxide.
Broken clays.
Broken edges of clays.
And organic matter or something.
The functional groups of organic matter. All right, way to go, Nathan. That's what's up. Functional groups of organic matter, aluminum and iron oxides, broken edges of clays. My professor asks us that every single day for like a whole month. What is the fate of nitrogen? So that it automatically rolls off of my tongue without ever thinking about it. Fixation, immobilization, mineralization. right? Ammonification, nitrification, denitrification, volatilization. Like, you just have to go over that constantly. I would make note cards, and then I guess today you can actually do voice recordings of your note cards and listen to them when you're driving or however it is. What is the fate of nitrogen? I know y'all are sick and tired of hearing that, but you at least get half of it. So, get a soil test, add lime, soil becomes more alkaline, hydrogens dissociate from the functional groups of organic matter to form water, leaving negative charges. As we form this water, that water is in soil solution. We add our fertilizer, and undergoes the nitrification process, which is an oxidation. And oxidation, it loses. We'll lose hydrogens. So that hydrogen loss adds that to the soil, which decreases the pH and making it more acidic. So at the end of the growing season, what do we do again? Put more lime out, because we know we're going to need it. We automatically know. You can almost technically measure how much acidity you're going to have to overcome, how much acidity you're going to have to neutralize based on how much nitrogen you applied, which are growing season. There's some people out there who like doing that stuff. How about we're going to put 2 tons out in September or October, we'll come back and check it in February. So now we have this acidity. Some of those hydrogens will now associate with the negative charge in these functional groups of organic matter. Now we're back at equilibrium. So remember, we're trying to get back to equilibrium always. But remember, we have this reserve acidity or exchangeable acidity on those soil colloids, and they continue to supply hydrogens because we're still trying to get to equilibrium, and the soil is always negative. So now those colloids will give off some of the hydrogens in order to make this balance up for the ones that just associated back with the functional groups of organic matter. In certain cases, with very strongly alkaline, very strongly acidic soils, we can get this extra association here. Now, this is not water. It's not, right? Because water is a balanced molecule. And now we have a positive charge. And this is what we have in our oxasols, and we have in Brazil. They got a real big problem with this. They can throw lime at it, throw lime at it, throw lime at it, throw lime at it. Doesn't matter. Nothing that can be done about it. It sucks up the lime, and when they go to put phosphorus out, phosphate being a negative or an anion, it is attracted to this positive charge in this soil.
So do those never dissociate? They just stay?
It will depend on the equilibrium of the soil, right? So all of this and what's going on in the soil solution, excellent question, because that's exactly what soil chemistry is about. Everything that is going on here will dictate what happens here. Not only on organic matter, on our soils, period. Just your basic run-of-the-mill regular old cation exchange sites or anion exchange sites. It's just that when we get into these extremely or very strongly acidic soils, there is the potential for these hydrogens to, so this will be so positive and this be not as positive, that we're still trying to get to that equilibrium, and you know, these charges will change. Have y'all had organic? No? Okay. Tell you about organic. Don't. These bonds and these charges will change because we're trying to get to equilibrium, and so there might be the opportunity that these bonds shift, and there's an opportunity for the electronegativity of this oxygen or this hydroxyl on the end of this to at least be able to absorb another positive charge. Even if it's weakly bound, there's still that potential based on the changes in here. And if we have a change somewhere else in this functional group, or in this piece of organic matter, or in this one, or in that one, if we have a change, not that this happens all the time, what if just one of these came on? You see what I mean? Like, so it's not always consistently that these will come off. It's only based on what is in the soil solution, on how much dissociation happens. Also based on the type of the type of functional group, whether it's a carboxylic. This one would probably dissociate first over this one because this phenolic ring has more pull on this hydroxyl than just this one carbon and this one bond. Not to get too much into organic.
So the OH2 plus, when that forms, is that the big issue that they can't figure out a way to get that back to equilibrium? Is that the big problem with the oxasols? Is that what maybe I'm just confused?
No, so the oxasols and the deal with that is there's nothing left.
Okay.
Let me see if I got that in here. Aluminum and iron hydroxides. Okay? There's just nothing, there's nothing there. It's all aluminum. And this is a +3. And so when we have those functional groups of organic matter interacting with this, now these charges are affecting the charges on the functional groups of organic matter. And it's just kind of, there's a strong bond, and then all of a sudden something happens in this functional group of organic matter that's a weak bond, and a hydrogen just attaches. Kind of like right here. This is balanced, but in certain situations, this hydrogen can still bond with that water to form this hydronium. It's only going to happen for a split second, and then it's off. And then there's another hydrogen that's sitting there right behind it. Tag, you're in. And there's all these hydrogens going on around here, around all these water molecules that will attach. This is in water, okay? The difference in that here is that this is kind of at an equilibrium. So based on the equilibrium and the charge of the things that are going on in this organic matter, and here is organic matter. Now sure, there's a let's try and just consider kind of like right here and everything right here. When this shifts, and who knows why it does, when this turns, the force of attraction along this does change. Let's just, at very best, it does change. We don't know which way it changes. We don't know where it changes, but it does happen. This bond, so now just in this little region right here, some 1/2 or 1/4 of a charge changes, and we can get another hydrogen that just happens to be in the right place at the right time and says, boop, now I'm part of this molecule. Which now shifts it back to equilibrium the other way, and this now changes back and then kicks that hydrogen back off. The hydrogen dissociates. That's why I said soil chemistry is, you never win. You can never, because it changes in an instant. We have a basic general idea at best. I guess us as agronomists and land managers, soil chemists, they would kick me out of this classroom because they're like, you don't know what you're talking about. For the purposes of what we're doing at the undergraduate level and about to go out into our careers, having the understanding that this stuff never changes, it's constantly moving into equilibrium. from some change that happens in this big long chain of molecules. Typically something that is going to happen right in this small area that also may have happened as a chain reaction from some area up here. So organic matter chemistry, job security is the way I look at it. Like, you will constantly be trying to figure out an unsolvable puzzle. All right, so those cation exchange reactions, there's like 4 types that are just very basic kind of thought processes. We have reversibility, where we have a 1-for-1. We have, this could be a potassium plus cation. Those two will exchange for each other, which is reversible. And then they can also exchange back. And notice that we're in the soil solution, which is why that change can happen on that functional group of organic matter. Next, the charge equivalence. It will take 2 hydrogens in order to dissociate 1 calcium. Did y'all go over this?
Maybe a little bit.
Okay. The primary concept is that you can either get a 1-for-1, and this is also a charge association. Right? It takes 1 hydrogen to displace 1 to exchange with 1 sodium. Charge. And then it's reversible, that it can go back and forth. This can go back and forth too. That's what these arrows right here are. These are the equilibrium arrows. That this reaction is constantly happening, or has the potential to constantly be happening, right? Like, it's not that these 2 hydrogens and calciums are sitting playing tag back and forth. I have the ratio law. This is getting a little bit more into it, but you can see that we had a 4-to-1 calcium to magnesium on the soil colloid. And then if I guess we have 20 calcium and 5 magnesium, so the ratio is 4-to-1. Here the ratio is 4-to-1 on the colloid, and it's 4-to-1 in the soil. That's that whole matter cannot be created or destroyed. You couldn't have half of one and a part of a calcium and like, they have to be equal. That's what we call it, equilibrium. So these, did I leave one now? There was another one that is like complementary. Do I have that in there? Yeah, there it is. Okay. So the cations being adsorbed to the soil colloids are going to be based on the charge that it has, the valence of the cation. Now, I'm going to set this up for later on down the road when we talk about oxidation state. The oxidation state is going to change the valence on the cation. So, like iron can be either +3 or +2. The oxidation state of the system is going to determine which one is available, which one is in greater concentration. Calcium is going to be held greater than magnesium. These two are going to be equal, and both of those are greater than sodium. Because sodium has a greater affinity for water. Have y'all ever seen where they throw sodium into the river? I'm going to bring that up next time. To take a big chunk of sodium and throw it into water will cause a big explosion. So that's why this sodium is the least attractive to the soil colloid, because it's attracted to the water in the soil solution. Those little bitty water molecules, it's attracted to that. Charge and hydrated radius. And so with each one of these, there's a little small circle of water around each one. Sometimes there's a large, kind of like a hula hoop, or a, kind of like how Pigpen, you know, remember Peanuts, and Pigpen had that little dust cloud going around him? Each one of these cations has a little water molecule, like a water protective bubble, so to speak, that goes with each of those cations. So if we have a greater charge, like aluminum has a high charge and probably a small hydrated radius, and it's held very tightly to the soil colloid. So less water, greater charge, soil helps highly to the soil. We have a lower charge with a large hydrated radius. Remember, sodium has an affinity for water. It will have a large hydrated radius and a very small charge, so it is not held to the soil colloid as well or as tightly. And then finally, this complementary cations. There's just these affinities. Primarily, look at the charges being at least greater than 1, and these being, so these are on the left side of our lyotropic series. These are on the right side. They're also the ones that exchange the most. Calcium, sodium, and magnesium. Only one calcium came off of. Right. Not going to need to know that on an exam. I'm not going to ask you to draw this or explain it. Just understand that, like, there is this cation exchange capacity that are governed by these simple rules of chemistry. So we have two of these. When you send off your soil sample, there are going to be two pHs that come back. One will be a pH, and then one will be a buffer pH. And so what this is saying is that when you turn this soil into them, they measure it right then and there. And whatever that, like, that's what's going to be in the field as it stands. They'll change the pH, and as we increase our pH, we increase our. As pH increases, CEC goes up or down. Up, because of pH dependent charge, right? We're dissociating those hydrogens, leaving that negative charge. So what they'll do is they'll increase the pH to dissociate all those hydrogens off and see what you technically could hold in that soil. And if we have an acidic soil, we have less CEC. If we have an alkaline soil, we have a greater CEC. I'm going over this a million times, and that might just be because I spent like 3 hours making these slides, and I like watching those movements go. Greater pH, more alkaline, right? We have the dissociation. There's where we get our extra CEC from pH dependent charge. Now we have our acidic soils, and we have this. Come on, go, 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 go. The charge is now less because we don't have those negatives hanging out there anymore. So as pH increases, CEC increases. So alkaline, greater CEC. Acidic, lower CEC. Percent base saturation is something else that they use just to determine how many cations you can actually hold, and also what is there. So if you already have a lot of cations already on the soil, and you go to add a whole bunch of ammonium, what's going to happen? It's like trying to fill this cup up. If this cup is half full with base cations, I can only hold as much base cations, right? Because the CEC is only so much. I can only fit so much in this cup. Same thing with the percent base saturation. And that the CEC is going to vary among soil columns. That's why it's important to kind of know what your soil is. So if you have a kaolinite, a 1-to-1, you don't have much CEC. If you have a smectite, a 2-to-1, highly expanding like we have in the delta, they have a large CEC because of all the clay colloids there. Moving into anion exchange capacity, these are typically going to form some inner sphere complexes, and we're about to go over those in a second. But based on these negative charges, and they also have this, they also have that water bubble around them, and that interacts with the soil colloids and how well they're adsorbed to the soil. In our oxasols, what do we say our soils were more positive or negative? Remember, aluminum is a +3. So it would be more positive, right? Which means we would have a greater capacity to hang on to phosphate, sulfate, nitrate. So in oxasols, you can think about holding on to these O's. Sulfate, phosphate, nitrate, all your 8s. So this, remember I mentioned kind of in the beginning this ionic, the diffuse double layer. Here we have our negative colloid, so our colloid with our negative charge. We have all of these cations vying for a spot with this electronegativity, and as we start to get away from the soil colloid, I'm going to bring some magnets next time. This over here is very loosely and very kind of, it is not influenced by this necessarily. This negative charge has nothing to do with it because it's too far away, right? The electronegativity of this does not have any influence on that. But also at the same point in time, and I was explaining this to my soils class, think about when you're, pre-COVID, when we went into, let's say a football game or a basketball game, and you go into a concert. And we don't all just line up perfectly 1 foot away from each other and all walk in unison in there, right? Like we're all just kind of standing there. We might move over here a little bit, might back up, and kind of go over here. We're all going to make it in. And then when we get into the concert, we're down on we're trying to get our picture taken, and we're moving, and then there's movement over here. The same thing is going to happen with this. This positive one might move over here. And then this one might move there, and that one might move there. And then if we get enough change, if these two move and this negative one comes over, these two will come up with it. And then we'll get some other shift, and then these will come over here. So this is constantly moving based on the charge right here and this diffuse double layer to diffuse double layer. And this is going to increase and decrease with temperature. Because remember, the more cold it gets, everything slows down, right? So this right here will contract, and these aren't moving as much. So like there's no movement inside this diffuse double layer. As the temperature warms up and we put a little bit of water in here, all of a sudden things kind of open up, and there's this, I guess the best way to say it is like it's kind of slippery. And there's water movement, and you start to get these cations that will move and flow and kind of bounce off of something, and they're not very stationary and stable. Again, it's one of those things that they study with different soils. They know, we're talking angstroms. I don't know if any of y'all have ever heard of an angstrom, but it's super freaking small. Electron microscope type stuff. When I'm sitting in, I actually learned this in advanced fertility. I just called him out. I was like, wait a minute, you've never seen this before? No, we haven't. Someone else has with a scanning electron microscope in the 70s, and I was like, they weren't even good back then. So you don't know that this is true. Get out of my class. That's what he told me. He said, get up, get out. But just to understand that there are people who are studying these things at the very minute microscopic level. So the difference between an outer sphere complex and inner sphere complex is going to be water. Easily exchanged because we have a water molecule between the soil colloid and the cation. So that's kind of where the electronegativity is decreased. Think about the space that it would take up. Like we had before, where we had this negative on the soil colloid. I'm probably going a little closer. So this goes back to the hydrated radius and the charge. The distance between the center of this atom, where the charge actually is further away from the negative magnet. Basically, magnets is the best way to put that together. So the further away it is, the less strongly it's absorbed. Inner sphere complexes are different because that water molecule is not there, but might be. There's still going to be water inside of those inner layer structures. So here we have these diffuse ions. Here we are with chlorine with this water molecule around it. Very similar to this. We have magnesium with a water molecule, with water molecules surrounding it. So molecules. The inner sphere complex is going to be the charge between this hydrogen on one water molecule and the hydroxyl as part of, let's say this is probably actually gibbsite or kaolinite. So this would be a tetrahedral layer. So the hydrogen bonding that occurs between these two, again, that charge is going to come down to a half of a charge between the two of them, and the hydrogen is going to bond that to the outer sphere, the outside of the tetrahedral layer. What we're going to have here is we're going to have this, for inner sphere complexes, we're going to have this change where these hydrogens, and this aluminum is now causing this greater charge between, I would write on the screen if I could, +3, Al3 plus, and this is a negative charge. Overall, this is negatively charged. So these two being +6, there's being a -4 right here, actually 8. Phosphorus being 4, depending on the oxidation state, and now it is bonded with the inner sphere ions. This outside, the broken edges of clays, if you could want to think about it like that, the edge of the clay, outside, the inside of the clay, inner sphere and outer sphere. We're not going to talk a whole lot about that when you start getting into, that's very scientific soil chemistry. We're trying to understand how our anions, cations, and then we're also going to go into pesticides, about how they bond with the soil, knowing if they're going to form a outer sphere complex, which means they are not strongly adsorbed to the soil, or if they form an inner sphere complex, meaning they are strongly adsorbed to the soil. That's pretty much the basic practical application of this concept. Outside, easily absorbed. It doesn't take much to detach this, because there's only 2 hydrogen bonds there. This is 2 negatives and 2 hydrogens. That is easily overcome. On this inside, we've got, well, 6 bonded with these oxygens and this overall molecule, and that charge is greater, and the bond between these two is greater compared to the bond between these two. Making sense? I think this is the last slide that I have. Oh. Again, this is going to be based on, this is where your pesticides and the adsorption, complexation, and partitioning, that kind of goes in environmental fate and transport, and I'll try to get some sort of presentation that is not a whole class, because it can be, the chemistry in that gets just too crazy. And the good thing about it is I've been through it, and I know what you do and you don't need, and what you do and don't need to understand. Okay? See if I can find a sodium and water video.